In 2017, an international group of scientists discovered 7 Earth-like planets. Just imagine 7 rocky planets similar to Earth, and they all orbit a single star, which is only 39 light-years away. That's practically around the corner by cosmic standards. Astronomers are confident that very soon, using data from telescopes, they will be able to say for sure whether these planets have an atmosphere and if it contains water, vapor. And since water is a universal solvent in which the organic substances that build DNA molecules can mix, scientists may be able to show that conditions for life are found everywhere in the universe. It is possible that in the near future, the holy grail of planetary astronomy will be found, an Earth twin in open space. Around the same time, astronomers found another Earth-like planet, Proxima Centauri b, and it orbits the star closest to us, just 4 light-years from the Sun. That is, it is literally our cosmic neighbor, and it is also in the habitable zone, where liquid water can exist. All these discoveries are just a few new entries in a vast encyclopedia already containing over 5,000. World media reported another breakthrough in astronomy. Scientists obtained the first photograph of a black hole. Yes, that image where a red ring of gas spirals around a black shadow in the center. Billions of people have seen it. Black holes were predicted mathematically as a consequence of Einstein's equations over 100 years ago, and the photo confirmed that these initially unimaginable objects do indeed exist in space. By the way, this photographed black hole is monstrously huge. It is 6 billion times heavier than the Sun. Personally, its photo reminded me of the Eye of Sauron from The Lord of the Rings. Only this eye is real and the size of our solar system. To obtain this unique image, astronomers created a most powerful super telescope by combining data in comparison to the James Webb Space Telescope, which was launched at the end of 2021. In just its first year of operation, it sent back such images of distant galaxies that astronomers' jaws dropped. This is what the universe looked like over 13 billion years ago, shortly after the Big Bang. We see the very first galaxies, young, with irregular shapes. The light from them traveled to us several times longer than our planet has existed. And here is another image, no less interesting. The Ring Nebula. These are the remains of a dying star that shed its outer layers. Only thanks to the incredible clarity of the Webb images did the finest details become visible. Vortices and swirls of gas. Thus, astronomers saw for the first time what a star looks like at the moment of its death. And this is just the beginning. The Webb telescope will operate for many more years, regularly showing us new corners of the universe. And there are dozens of other observatories around the world and in space. All of them tirelessly scan the sky, collecting gigabytes of data to then assemble them into a unified picture of the universe. Is incredibly diverse. It has everything. From the smallest particles to giant clusters of galaxies, from the deserts of Mars to, possibly, oceans teeming with life on exoplanets. But do you know what is most surprising? All this magnificence obeys the same laws of physics. Laws that the human mind is capable of discovering and understanding. It's simply amazing how far we've progressed from primitive myths to modern astrophysics. By studying space, we better understand not only the universe around us, but also ourselves. After all, we are all children of the stars, literally. Every atom in our body was once created in the thermonuclear furnace. How did humans begin to build a picture of the world in their minds, starting only from simple observations? This adventure of human thought is described in the book by astronomer Sergei Vyazev. The Universe. A Journey Through Time and Space, and the book by theoretical physicist Michio Kaku, The God Equation. They have inspired this exploration. Let's together embark on this journey spanning thousands of years, from the primitive cosmology of ancient civilizations to the latest theories of the origin and evolution. Imagine yourselves as inhabitants of ancient Greece. If you had no knowledge of the world around you, how would you perceive the universe? You stand on solid ground, which, frankly, is flat, not counting mountains and valleys. Above you is a blue sky, with the sun, moon, and stars. Your life unfolds amidst wild nature, forests, steppes, rivers, and mountains. Every day, a dazzling bright circle, the sun, rises on the eastern edge of the sky. It gives the earth light and warmth, determining the rhythm of all living things. The sun makes its eternal journey, rising to its zenith, and then descending beyond the horizon. It is the solar cycle that underlies the biological clocks of all inhabitants of the planet. As the luminary sets, the world plunges into darkness and cold. Myriads of stars appear in the sky, and their pattern remains unchanged from night to night. Observant earthlings group them into memorable patterns, constellations. This helps to navigate in space, 5 particularly bright stars change their position, tracing bizarre loops in the sky. They are called planets after powerful deities: Mercury, Venus, Mars, Jupiter, and Saturn. All these phenomena, well known to modern man, held many mysteries in antiquity. However, they were part of everyday life. Hunting, agriculture, and survival in general depended on them. The first thing people learned was the change of seasons. It turned out that the natural cycles associated with it were not a whim of chance, but rules. Spring was always followed by summer, but never by winter. And so, year after year, with the development of speech and abstract thinking, people began to delve deeper into the essence of the surrounding world. At first, they simply noticed sequential events. Sunset is followed by night. But then came an epiphany. It gets dark precisely because the sun has set. Day changes to night not by chance, but according to a strict world consisted of 4 elements: earth, water, air, and fire. In China, wood and metal were added to this. All substances around were supposedly created from the mixing of these elements, and various gods controlled them. It was logical to assume that the earth was a flat disk covered by a dome of the sky. In some places, the disk is filled with water, but even under the water, there's a solid bottom. Rain sometimes falls from the sky. Apparently, there is a supply of water there. The sun and moon move across the sky, and the stars look like holes in the celestial vault, letting in external light. The same picture of the world was described in the Old Testament. God created the firmament, separating the earthly waters from the heavenly ones. On the firmament, he placed the luminaries, the sun, moon, and stars. Few disputed these ideas, as they coincided with the visible picture. Why not? There was also a belief that the massive earth rested on some supports: elephants, turtles, bulls, and what have you. The movement of these creatures explained earthquakes. The earth could float in a world ocean, or be attached to the sky by chains. A Muslim myth depicted a complex structure of an angel, a bull, a vessel, and a fish on which the earth rests. According to a Slavic legend, an oak tree and whales in a fiery sea played the role of supports. This is an important point. Authors of cosmological concepts could pile one support for the earth on top of another, but somewhere this process had to stop. Otherwise, the supports would multiply indefinitely. Sooner or later, thinkers realized that the will of higher powers was indispensable here. Although if divine intervention was still required, it was more logical to resort to it immediately. Making the earth simply float in space was the ancient Greek philosopher Anaximander in the 6th century BC. In his model, the cylindrical earth simply hung motionless in the center of the cosmos. The explanation was brilliantly simple. The earth had no reason to move in any direction since it was already in the center. To realize that the huge earth with all its continents and oceans could freely rest in the void was a huge intellectual breakthrough. For however absurd this thought might be for the common person, it is still more reasonable than Anaximander was the first to suggest that celestial bodies are at different distances from Earth. In his opinion, a certain primordial substance first existed, a peiron. It separated into a cold core and a fiery shell. From the heat, the shell disintegrated into several rings. In the nearest ring were stars, holes through which fire was visible. In the next ring was a larger slit, the moon. And in the farthest ring was a hole the size of the Earth, that is, the sun. At the very heart of the universe, the Earth arose, resembling a flattened cylinder. Its surface was covered with moist primeval ooze, in which a real miracle occurred. The first living creatures originated in it. They resembled fish and evolving came out onto land, and from these amazing creatures, the first humans were formed, leaving their fish cradles. Essentially, this was the first geocentric system of the world. Of course, all this is no more than a beautiful fairy tale, but you must agree, for those times it was impressive. They did without gods, explained the earth, life, and man. But alas, this hypothesis could neither be proven, and Heraclitus developed this idea, adding new details. They were united by a materialistic view of the universe. The world explains itself without reference to gods. Heraclitus, for example, proclaimed sight and hearing as the main cosmology of the great mathematician Pythagoras. In the 6th century BC, Pythagoreans believed that the universe was governed by the mathematical harmony of whole numbers. Thus, Pythagoras discovered that the sounds of an octave are born when a string is divided in ratios of 1 to 2, 2 to 3, 3 to 4, and so on. That is, musical intervals are set by simple numerical ratios. For Pythagoras, this meant that pure mathematics lay at the heart of the cosmos. Hence his famous, all is number. How did Pythagoras envision the universe? In the center of the universe floated a mysterious central fire, Hestia. Around it, the Earth, Moon, Sun, and 5 known planets orbited. Between the Earth and Hestia circled a mysterious anti-Earth, forever hiding the central luminary from us. Beyond Saturn followed the sphere of fixed stars. There were a total of 10 celestial spheres, an ideal number for Pythagoras. It is noteworthy that Pythagoras did not think that celestial bodies fly in a void. They were supposed to be attached to giant crystal spheres, nested one inside the other. Rotating at different speeds, these spheres carried the planets and stars, and also produced music, a specific note for each. We do not hear this harmony of the spheres only because we were born in it and perceive it as silence. Of course, Pythagoras' system was also speculative, like all the previous ones. Spherical Earths, crystal spheres anti-Earth. All these are no more than guesses, but here for the first time the planets were named in the correct order, and it was shown that the Earth is not the center of the world, but merely one of the celestial bodies revolving around something else, even if not the sun. Pythagoras' followers even explained the change of day and night by the Earth's rotation. This is practically Copernicus. As early as 25 centuries ago, the best minds of humanity began to seriously ponder the structure of the cosmos. Albeit purely intuitively and without reliance on experience, insights deeper than tales of Earth on whales were made even then. What unites all these theories of the ancient world, from the biblical to the Pythagorean? You've probably guessed it. That's right, they were mostly made up. Well, yes, although they were based on observations, much was conjectured. In the end, all of this turned out to be incorrect. Neither a flat Earth, nor a celestial firmament, nor crystal spheres admitting to distinguish truth from fiction. Apparently, it was the emergence of critical thinking, upon which the scientific method grew. Humans began to analyze their own ideas, asking themselves, why do I think so? Can I think differently? What if lightning is not Zeus's anger? It was critical thinking that became the engine of civilization's progress. Take, for example, the ancient texts of Egypt and Babylon. There was nothing like mathematical proofs there. The very concept was absent. Proofs appeared in ancient Greece more than 2,500 years ago, probably thanks to the birth of democracy. In disputes among equal aristocrats, logic, different points of view, and their argumentation were required. The one with the better arguments won, not the one with a laurel wreath on his head. The transfer of the practice of proof to mathematics led to the appearance of theorems. Thales was already proving the statement about the equality of angles at the base of an isosceles triangle. Mathematics was considered a noble pursuit, a kind of elite club. It is not surprising that the Greeks soon developed. Aristotle was one of those who applied a scientific approach to the structure of the universe. Studying the moon, he understood the nature of its phases. The moon is a sphere onto which sunlight falls. Observing the moon occulting Mars, Aristotle concluded that planets are located farther than the moon and stars farther than the sun. But that's not all. Aristotle also had 3 arguments in favor of the Earth's sphericity. Firstly, when a ship moves away from the shore, its lower part disappears first, then the middle, and only then the sail. This is possible only if the surface of the sea is convex. Secondly, lunar eclipses occur when the Earth is between the sun and the moon, and the Earth's shadow on the moon always has a rounded shape. Thirdly, when an observer moves north, the North Star rises towards the zenith. This again indicates the curvature of the Earth's surface. Based on these facts, Aristotle logically impeccably proved that the Earth has the shape of a sphere. True, he was slightly mistaken in thinking that the Earth was the center of the universe. But here, too, he proceeded from observations. If the Earth moved around the sun, he reasoned, then we would see the displacement of stars. But stars are so distant that these tiny displacements were measured only in the 19th century. In Aristotle's time, Aristotle's ideas were embodied in Ptolemy's system. He wondered how to reconcile theory with what we see in the sky. He had to develop a complex system of epicycles, that is, circles along which celestial bodies moved, and deferents, other circles along which the centers of the epicycles moved. Yes, the system was exactly as complicated as it sounds. Epicycles in deferents, deferents in epicycles. Perhaps Ptolemy invented not only the geocentric system, but also the world's first Matryoshka doll. The radii and speeds of movement along the circles were chosen so that the result corresponded as much as possible to observations. For a better match, the system had to be stuffed with dozens of epicycles. Despite its contrived nature, Ptolemy's system excellently predicted the position of planets for a year ahead. And Ptolemy did not just consider the Earth stationary for no reason. He was a brilliant scientist and knew about centrifugal force and inertia, but without precise formulas and experiments, he could not assess their effect. He reasoned thus: if the Earth rotated, then all falling objects and clouds would lag behind, carried by inertia. A stone dropped into a deep mine would hit the wall. 1,700 years later, Benzenberg's experiment proved that this effect does indeed exist due to the planet's rotation, albeit very small. Ptolemy's system was based not on guesses, but on strict logic and observational data, and this distinguished it from previous world pictures. Eventually, science itself, by testing and perfecting itself, later refuted this model. But before that, Ptolemy's system dominated observations made by the Greeks 2,000 years ago, it followed that a spherical, stationary Earth was at the center of the world. Did no one question this? There were such daredevils, for example, Aristarchus of Samos, who long before Ptolemy proposed a method for measuring distances to the sun and moon. Observing the moon in its first or last quarter phase, when we see exactly half of its disk, Aristarchus reasoned as follows. The angle between the Earth-Moon and Moon-Sun directions is a right angle. Therefore, the ratio of the Earth-Moon distance to the Earth-Sun distance is equal to the cosine of the angle between the directions to them, and it can be measured. Having made such measurements, Aristarchus found that the sun is 20 times farther than the moon. In reality, it is 400 times, but for those methods it was a decent estimate, and since the apparent sizes of the sun and moon are approximately equal, the sun must be 20 times larger than the moon. By comparing the apparent sizes of the Earth's shadow on the moon during eclipses, Aristarchus calculated that the Earth is about 3.5 times larger than the moon, which is close to the truth. From this, it followed that the sun is about 6 times larger than the Earth, that is, hundreds of times larger by volume. But the most interesting part is ahead. The colossal size of the sun led Aristarchus to the idea of a heliocentric system of the world. It is more logical that the huge sun would be at the center and the smaller Earth would revolve around it. Confirmation came from changes in the brightness of Mars, inexplicable in the geocentric model. The displacement of stars during Earth's movement is not visible simply because they are incredibly far away, Aristarchus asserted, and he was absolutely right. But at that time, his hypothesis could not yet compete with the well-ordered and after the decline of ancient civilization and the onset of the Middle Ages. The understanding of the universe's structure not only did not develop, but also lost its previous achievements. Christianity brought a different spirit of the times. The need for research into the world beyond the Bible was questioned. The works of ancient thinkers were often destroyed. In the Library of Alexandria, they were burned to the ground, along with thousands of priceless books and manuscripts. Want to ask an inconvenient question? Welcome to the stake. The main picture of the world for Christians in the 6th century became the primitive scheme of Cosmos Indicopleustes, a flat, quadrangular Earth, surrounded by walls and covered by a solid celestial vault. Night falls when the sun hides behind a high northern mountain. The idea of a spherical Earth was initially ridiculed. How can people on the other side walk upside down? Subsequently, Aristotle's teachings were accepted by the Church, but selectively. The idea of the Earth's central position as God's main creation fully corresponded to biblical notions. And why not? It's logical, isn't it? The Earth is flat and rests in the center of the world. The Earth is the crown of God's creation, no less. All according to the Bible, you can't find fault. The spirit of inquiry, Aristotle's call to study the world through observation, was forgotten. Scientists' treatises were simply memorized without analysis or criticism. Independent thought was not encouraged and was under threat of accusation of heresy. It is not surprising that not a single astronomical discovery was made in Europe. Did astronomy move from a standstill? And do you know who had the courage to revive the heliocentric idea? A priest? Imagine Nicholas Copernicus sitting in a monastery, studying ancient folios, and at some point it dawns on him, wow, this is it all fits. The sun is at the center and the Earth revolves around it. The Earth, moreover, rotates on its axis. All this immediately explained the loop-like movements of the planets, but Copernicus was in no hurry to shout about his discovery from the rooftops. Of course, he spent 40 years to verify everything and leave no loopholes for criticism. He followed Ptolemy's structure, but used fewer epicycles in combination with deference instead of cumbersome ones. Most importantly, Copernicus swapped the Earth and the Sun, making the latter the center of the system. The planets were attached to transparent solid spheres, nested one inside the other. All the stars were on the largest sphere surrounding the solar system, just like wallpaper on walls. In general, Copernicus's work was quite a tome. Not everyone could master it, and its predictions were worse than Ptolemy's system, but his main ideas instantly spread throughout Europe. It was a real breakthrough. It's just a pity that Copernicus himself did not live to see the publication of his work. The man was not allowed to enjoy which received the name Copernican Revolution, was truly revolutionary. Just think about it. The Earth moved from the center of the universe to somewhere on the outskirts, becoming just one of many planets. Humanity lost its privileged position in the world. What a blow to self-esteem. This transition dragged on for many years and was not easy. It would seem that no new evidence in favor of heliocentrism appeared then. All the arguments cited by Copernicus had already been voiced earlier, for example, by Aristarchus of Samos. The Catholic Church initially reacted calmly to the heliocentric model, seeing it only as a convenient method of calculation, but soon it sensed an unpleasant heretical whiff in the idea of displacing the Earth from the center of the universe. The situation was especially aggravated by the fervent supporter of Copernicus's ideas, Giordano Bruno, who openly criticized church dogmas. Let's just say he added fuel to the fire. In his opinion, the universe is infinite and filled with many worlds similar to the solar system. Stars are distant suns around which planets also revolve, possibly inhabited. Such bold ideas of a multiplicity of worlds could not please the church. The outcome is sad. In 1600, Bruno was burned at the stake. Copernicus's work on the revolutions of the celestial spheres was included in the Index of Forbidden Books in 1616. It seemed that heliocentrism... In 1609, Galileo Galilei, inspired by the Dutch spyglass, built a telescope and pointed it at the sky. Discoveries poured in one after another. Galileo discovered that Venus has phases, like the moon, which means it orbits the sun. Jupiter's moons clearly orbited that planet, not Earth. These were irrefutable proofs of the validity of the heliocentric system. So why did Copernicus's idea eventually win, despite all the power of the church? It seems it was due to another change in the spirit of the times. The life of Europeans in the 17th century was full of hardships and upheavals. The familiar medieval order was collapsing. Religious wars were raging. Epidemics were rampant. You must agree, in such an environment, it is difficult to feel like the pinnacle of creation, living in the ideal center of the universe. Rather, the Earth, ravaged by disasters, turned out to be a godforsaken periphery. Far from perfection, the place in the center of the universe was more suited to the sun, the ideal, eternal source of light and heat. Thus, public consciousness, gripped by crisis, turned out to be psychologically ready to clear and logical picture of the world. There was still one more obstacle. The idea of the uniform motion of planets in perfect circles. It was precisely to explain the visible deviations from it that ancient and medieval astronomers constructed unimaginable intricacies of epicycles and deferents, and even Copernicus could not completely abandon them. Only at the beginning of the 17th century did the brilliant Johannes Kepler, after analyzing the most precise data from astronomer Tycho Brahe on the motion of Mars, discover his famous laws. It turned out that planets move around the sun not in circles but in ellipses. Moreover, the speed of a planet is not constant. The closer to the star, the higher it is. Kepler's laws described the observed movements of planets with amazing accuracy, without any of those cycles and epicycles, confirming and supplementing Copernicus's heliocentric system. It is not without reason that they are often called the final chord of the Copernican revolution. But the pinnacle of this revolution was the concept of the infinity. Nicholas of Cusa argued that in an infinite universe, there can be no absolute center, neither in the form of the Earth nor the Sun. He Pascal the existence of countless worlds. Giordano Bruno developed these ideas, stating that only an infinite universe with an innumerable number of star worlds, many of which may also be inhabited, can correspond to the greatness of the Creator. Imagining infinity is easier than it seems. We encounter it from childhood. For example, there is no largest prime number, because one can always be added to any number. A spacecraft will never hit a wall with the inscription, "End of the world," and no matter how much time passes, the next moment will always come. In my opinion, it is more difficult to imagine a finite universe than an infinite one. Such a picture of the world broke the usual ideas about solid celestial spheres and the dome of fixed stars, because infinite space does not need material support. In essence, critical reflection showed that if the Earth is capable of freely floating in space, then why can't other celestial bodies float in the same way? Even in the first pictures of the world, it was necessary to introduce God's will, simply to interrupt the endless series of celestial spheres or cosmic turtles. So here too, no matter how the church suppressed free thought, the idea of an infinite universe inevitably sprouted. For a long time, people were interested in the question of what forces set celestial bodies in motion. Some believed that the luminaries moved by themselves, being alive. Others believed that spirits, angels, or gods controlled them. But centuries passed, and all these supernatural explanations somehow lost their persuasiveness. People got used to the idea that impersonal natural forces, the laws of nature, operate in the world. Kepler, who discovered the laws of planetary motion, suggested that the speed of a planet decreases with distance from the sun, because the source of the driving force is contained within it. William Gilbert, a contemporary of Kepler, studied magnetism and suggested that the Earth is a giant magnet. This was indicated by the behavior of the needle of the compass, invented by Gilbert. And magnetism is a universal force in the universe. In the early 17th century, it was even discussed whether the Earth rotates due to magnetic forces and whether the moon affects tides through magnetism. In 1609, Kepler went even further. What if the sun is also a magnet, and its rotation creates a vortex in the ether, causing planets to move around the sun slower the farther they are from it? Descartes went even further, imagining the universe as a multitude of ethereal vortices with stars at their centers. Although these ideas turned out to be incorrect, it was later confirmed that the sun is indeed a magnet, and its magnetic field rotates with it. The nature of the planets governing the universe was revealed by the brilliant Isaac Newton. He guessed that the force holding the moon in orbit and the force attracting a thrown apple to the Earth are one and the same. After all, if the moon suddenly stopped, it would fall to Earth like an apple. It's just that the moon has a huge orbital velocity, thanks to which it constantly, as it were, misses the Earth. Can we turn an apple into a moon by giving it a high enough speed? Newton understood. Yes, easily. Continuously falling, it will orbit the Earth, becoming its satellite. Imagine a cannon firing horizontally from a high mountain where there is no air and friction. If you increase the speed of the projectile, it will fall to Earth farther and farther from the cannon. At a certain speed, the projectile will not fall, but will continuously orbit the Earth in a circular orbit like a satellite. This speed was called the first cosmic velocity. If the projectile is launched at a speed higher than the first cosmic velocity, it will begin to move in an orbit in the shape of an elongated ellipse. With increasing speed, this ellipse will become more and more elongated. When the speed reaches the second cosmic velocity, the projectile will leave the Earth forever. Thus, Newton discovered the universal law of gravitation, according to which gravitation is noticeable when at least one mass is enormous, like that of the Earth, but it acts between any bodies, obeying a strict formula. Studying the motion of the moon, Newton mathematically derived this law, and then it turned out that all three of Kepler's laws are simply a consequence of it. The theory of gravitation worked like clockwork, allowing orbits of planets and spacecraft to be calculated with enormous accuracy. Establishing Newton's theory was played by comets. Analyzing their movement, astronomer Edmund Halley established that the trajectories of comets are greatly elongated ellipses that intersect the orbits of planets. If crystal spheres existed, comets would inevitably collide with them, but nothing of the sort was observed. Thus, comets shattered the crystal spheres to smithereens. As a result, by the 18th century, enlightened humanity accepted a new picture of the world. The universe was seen as an infinite space, inhabited by a multitude of stars with planetary systems similar to our solar system. A single law of gravitation acted throughout the cosmos, and time flowed uniformly everywhere. Of course, mysteries remained. For example, why do planets rotate in one direction around the sun, and also almost in the same plane, unlike the chaotic movement of comets? Unable to find an explanation for this, even Newton resorted to the idea of divine design. Telescopes, astronomers obtained more and more data about distant objects in the universe. And what did they see? It seemed that nothing globally changes there at all. On Earth, seasons changed. Planets and comets circled around the sun. Stars twinkled in the distance. The cosmos looked stationary, as physicists say, unchanging over time. Perhaps individual stars faded, but new ones lit up to replace them, and many believed that it would always be so. The universe will remain eternally unchanged, like an ocean where waves constantly replace each other, never leaving the surface, calm. Of course, even in the Middle Ages, thinkers allowed that the cosmos could evolve, but this idea was not in trend. Astronomers were rather trying to understand the properties of celestial bodies. Based on the postulate of the immutability, it was necessary to find out the distance to the stars. How to do this became clear back in antiquity. If you measure the position of a star many, many times over a year, then due to the Earth's revolution around the sun, the points on the celestial map will form a small ellipse, the star's annual parallax. The smaller it is, the farther the star. Alas, for a long time, parallax could not be detected even by great astronomers like Kepler and Herschel. The stars stubbornly remained motionless. Supporters of geocentrism rejoiced. Aha, there's an argument for a motionless Earth for you. But Copernicus and his followers did not give up and rightly objected. No, the stars are just incredibly far away. Only in 1838 did Friedrich Bessel, using the most precise Fraunhofer telescope, finally measure the parallax of one of the stars. It turned out to be at a distance of 10 light years, that is, hold on tight, 90 trillion kilometers. Soon Struve and Henderson made similar measurements. Thus a breach was made in the wall that had for centuries hidden the stellar distances from us. It turned out that even the nearest stars are light years away. Alpha Centauri is 4.3 light years away. Light takes 8.5 years to reach Sirius. But how far then does all Milky Way extend? A bright band girdling the entire sky. It was visible from both hemispheres of the Earth, which indicated that the Sun and other planets are inside a huge flat system of stars. This was called a galaxy. Democritus had already guessed that it was a cluster of stars, but only Galileo's telescope confirmed his correctness. I observed the nature and substance of the Milky Way. With the help of a telescope, it was possible to observe it in such detail and with such visual clarity that all disputes were resolved. The Milky Way is in fact nothing more than a mass of countless stars gathered in clusters. In the 17th and 18th centuries, astronomers using telescopes discovered many faintly glowing nebulous patches in the sky, which they called nebulae. It turned out that matter can be organized not only into stars and planets, but also into gigantic volumes of diffuse matter. Thomas Wright was the first to suggest that the stars of the Milky Way form a giant flat disk. Herschel and his sister Caroline scrupulously counted the stars all over Thesky. The result of their 20-year labor was a map of the galaxy, which for the first time showed its disk-like shape. But it turned out that the Milky Way is much more galaxy is a flat, unwinding spiral of hundreds of billions of stars with a bar in the center. 2 main arms branch into as many as 5. The diameter of this behemoth is 100,000 light-years, and its thickness is about 1,000. The Sun is located on the periphery of the galaxy, 26,000 light-years from the center, where a supermassive black hole of 4 million solar masses is hidden. So if you ever feel insignificant and peripheral, remember, even the Sun is just a provincial star on the outskirts of a galaxy. But this does not prevent it from being the center of our world and the source of life on Earth. But is our galaxy identical to the entire universe? After all, other nebulae of different forms are visible in the sky. Some, even in powerful telescopes, look like gas clouds, not clusters of stars. William Parsons, in his giant telescope, discerned among them spiral ones, similar to the structure of the Milky Way, only very distant. But where are they? In our galaxy or observing the Andromeda Nebula? The previous method of determining distances no longer worked here. Too far. However, astronomers found a new way thanks to a special type of star called Cepheids. These are stars that regularly change their brightness. They become brighter, then dimmer, and so on in a cycle. Astronomer Henrietta Leavitt in 1908 discovered that the maximum luminosity of a Cepheid is directly related to the duration of its brightness change cycle. This means that by knowing the period of a star's brightness change, one can accurately determine how bright it is at its brightest moment. This discovery allowed astronomers to measure the distance to stars that are very far from us. Hubble found several Cepheids in the Andromeda Nebula and calculated the distance to them. It was 2 million light-years, that is, 20 times the size of our galaxy. Thus, it was proven that the Andromeda Nebula is not some distant corner of the Milky Way, but a completely different galaxy, possibly similar to ours. For the first time, it became clear that the visible universe, French philosopher Auguste Comte made a strong assertion implying certain knowledge about stars was unattainable. But science coped with this too, thanks to the emergence of astrophysics. What can we observe and study on Earth from distant stars? Only light. Newton had already shown that sunlight contains waves of different lengths, from red to violet. Astrophysicists learned to decompose this light into a spectrum using spectroscopes. And the shape of the energy distribution curve in this spectrum allows for the precise determination of a star's temperature according to Wien's displacement law. The shorter the wavelength, the hotter the star. If the energy peak is in the blue region, it means the star's temperature is around 20,000 degrees Celsius. Our sun has its maximum in the green region, which corresponds to 6,000 degrees. Red stars are cooler, around 3,000, and these conclusions do not depend on the distance to the star. Experienced astronomers can even estimate a star's temperature by its color with the naked eye, but how can one be sure that the temperature obtained from the spectrum is correct? After all, you can't fly to distant stars with a thermometer, or can you? The laws of physics are universal. The relationship between the shape of the spectrum and the temperature of the source has been tested hundreds of times in laboratories. Mathematics and logic in physics work unequivocally. If the conclusions of a theory agree with experiments, then the theory is correct. And astrophysical methods yield results that also converge and predict new phenomena. If there were an error in analysis, also allows us to learn the chemical composition of stars from the dark absorption lines. Each element leaves a characteristic set of lines in the spectrum, its own fingerprint. The presence of lines of hydrogen, iron, calcium indicates the presence of these elements in the star's atmosphere. Their quantity can be estimated from the depth of the lines. By the way, this is precisely what allows us now to study the Doppler effects played a huge role. It turned out that the lines in the spectrum of light depend on the conditions at the place from which the light originated. Experiments showed that some absorption lines split into 2 or 3 under the action of a magnetic field in the light source. This phenomenon was named the Zeeman effect in honor of the physicist Peter Zeeman, who discovered it, one of the first Nobel laureates in physics. The detection of the Zeeman effect in the spectra of sunspots led to the discovery of magnetic fields on the sun. In 1842, physicist Christian Doppler also discovered an effect named after him. He noticed that the pitch of a whistle from an approaching train seems higher, and from a receding one, lower. This was confirmed by an experiment where an orchestra played on a moving platform, and people with musical hearing stood on the platform and detected the differences. A spectacular experiment, but what does it have to do with astronomy? French physicist Armand Fizeau proved that the Doppler effect applies not only to sound, but also to light. If a light source is moving away from us, the lines in its spectrum shift towards the red end, and the speed of recession can be determined by the magnitude of the shift. Measurements showed that the lines in the spectrum of the eastern edge of the sun have a blue shift, and the western edge, a red shift. This confirmed the sun's rotation and allowed its speed to be determined, which coincided with data from the 20th century. Astronomers had a powerful arsenal of methods for studying distant celestial objects. Huge telescopes equipped with spectrographs allowed for the determination of the composition, temperature, velocities, magnetism, sizes, and masses of stars, not to mention the orbits and properties of even invisible planets around other suns. It would seem that the rapid development of science, mathematics, physics, chemistry, and along with them, astronomy, had finally given humanity a clear picture of the world, in which only details remained to be clarified. But already in the 19th century, scientists began to receive signals that something was wrong with the picture of an eternal gravitational paradox. Think about it. If stars attract each other, why don't the distances between them change? It was believed that the attraction of an infinite number of luminaries from different sides was balanced, but upon closer examination, this is not so. Gravitation only works to bring masses closer, and repulsion was not known then. This means that stars must inevitably fall onto each other, and the closer they are, the faster they will do so. Over infinite time, they would have long ago merged into one super-dense lump, yet galaxies are scattered over enormous distances with no signs of convergence. Stars in a galaxy move fast enough not to fall into its center, a supermassive black hole. Their speeds exceed the first cosmic velocity. Everything that moves slower has already fallen into the center of the galaxy, and bodies flying faster than the second cosmic velocity have flown away. Our objects with speeds between the first and second cosmic velocities have remained in elliptical orbits, but neighboring galaxies, in most cases, do not move fast enough to avoid merging. Thus, the Milky Way and the Andromeda Nebula are flying towards each other, and in billions of years, they will inevitably merge into a supergalaxy. The question arose, if the universe is infinite and eternal, why haven't all massive objects merged into one huge lump yet? After all, over infinite time, any process should have time to complete. This paradox showed that something doesn't add up in the picture of an eternal and photometric paradox. Imagine you are in an infinite forest. Wherever you look, there are trees, right? So in an infinite universe, we should see stars in every direction. Then the whole sky would shine brighter than the Milky Way without a single dark spot. Even cosmic dust wouldn't help. Over eternity, it would have heated up from starlight and started glowing itself. It turns out that the black sky is just holes between the stars. And that means their number is not infinite. At the turn of the 19th and 20th centuries, a real revolution took place in science. The discovery of X-rays, capable of penetrating opaque objects, overturned many provisions of classical physics. The phenomenon of radioactivity was identified. Scientists delved into the deep structure of matter and figured out the structure of atoms, which Democritus had brilliantly guessed at. It turned out that atoms consist of heavy, positively charged nuclei around which light, negatively charged electrons swarm. In the nucleus itself are protons and uncharged neutrons. Amazingly, new scientific instruments made it possible to detect individual electrons smaller than 1/100 billionth of a centimeter and even study their properties. Was unraveled. That's progress. James Clerk Maxwell created the theory of electromagnetism, showing the inseparable connection between electricity and magnetism. He reduced all known properties of electromagnetic phenomena to 4 equations. From them followed something amazing. Light is an electromagnetic wave traveling in a vacuum at a constant speed. But what then oscillates in a vacuum? The concept of a field had to be introduced. A magnet or charge seems to endow every point in space with a special property, to attract or repel. And these properties of the electromagnetic field are described by Maxwell's equations. And also, these equations contained a mysterious constant c, the speed of electromagnetic waves in a vacuum. Amazingly, it was exactly equal to the speed of light. Thus, the guess that light has an electromagnetic nature was brilliantly confirmed. This discovery simply blew minds. The universe turned out to be permeated by an invisible network of fields, electromagnetic and gravitational, and the propagation of light finally received a clear explanation. Photons are quanta of the electromagnetic field. Its waves are the very light that brings us all information about distant galaxies. The world turned out to be invisibly richer and more complex, which presented the speed of light as a fundamental constant, deeply impressed the young Albert Einstein. In 1905, he published an article outlining the basics of the special theory of relativity. Motion is relative. All physical laws look the same for observers moving uniformly and rectilinearly, regardless of speed, and the speed of light in a vacuum is constant in any frame of reference. That is, according to Einstein, all laws of physics are the same for observers moving uniformly and rectilinearly, and the speed of light is always constant. It seems simple, but the consequences? Phew, listen carefully, this is intense. For example, if you throw a ball on a train in the direction of its movement, the speed of the ball is equal to the sum of the speeds of the train and that ball. By this logic, a laser beam emitted from the side of a starship should propagate faster than the speed of light due to the ship's speed. But no, the laser beam will travel at the same speed of light as for a stationary observer, no faster. This means that time and distance flow differently for them. To explain this, Einstein suggested that clocks on the starship run slower and the ship itself contracts in the direction of motion. The crew would notice nothing. For them, everything would be as before. Nonsense? Not at all. Experiments confirm this. The speed of light is the same for approaching and receding stars, and clocks on satellites really do lag behind those on Earth. It turns out the world is not at all like Newton's, where time flows the same everywhere. For Einstein, space and time are relative. They depend on speed. He generally considered them a single whole, a four-dimensional continuum, and only all four coordinates together, 3 spatial dimensions and 1 temporal, completely determine the location of an event in the universe. Now you know the secret of eternal youth. You just need to fly at the speed of light. The theory of relativity showed that the speed of light is the limit. It cannot be exceeded, not at all. For example, if you weigh 70 kilograms and develop a speed of 90% of the speed of light, you will weigh 160 kilograms. If 99%, then about 500 kilograms. And if you accelerate a little more, less than 1% to 99.99%, then your mass will already be 5 tons. As you approach the speed of light, mass increases to infinity, so it's impossible to accelerate further. Only gravitational waves or massless particles like photons always travel at the speed of light. Finally, Einstein lifted the veil of mystery over the nature of energy. It turns out it's not just about mechanical work. There's also thermal energy and the energy of particle interaction. As Richard Feynman, whom you know well, aptly put it, there's a certain quantity called energy, which does not change during any transformations occurring in nature. This is essentially a mathematical principle stating that there is some numerical quantity that does not change under any circumstances. This is by no means a description of the mechanism of a phenomenon or something concrete. It simply notes the strange circumstance that one can calculate some number and then calmly watch nature perform any of its tricks, and then calculate this number again, and it will remain the same. Einstein derived the famous formula linking the total energy of a body and its mass. E equals mc squared. Its meaning is that mass is, in essence, a reserve of energy, and an incredible one at that. Even in a tiny piece of matter, there is energy like in an atomic bomb. 1 gram is 20 kilotons of TNT. True, to release this energy, annihilation is needed. This is when a particle meets an antiparticle, and they turn into pure radiation. Mass disappears, but a lot of photons appear. By the way, 30 years after Einstein, his formula explained where stellar energy comes from. It turns out that in the depths of stars, hydrogen turns into helium. But the mass of the resulting helium is slightly less than that of the original hydrogen, and this excess mass becomes radiation, starlight. Every second, millions of tons of hydrogen in physics was brought about by the general theory of relativity. Its essence is simple, space-time and matter are inextricably linked. Masses curve space, and it affects the motion of bodies and the passage of time. It sounds wild, but it's true. Imagine space as a trampoline. Place a heavy ball on it. It will bend the surface. The heavier the ball, the stronger the bend. Now roll small balls across the trampoline. They no longer roll straight, but go around the massive object in an arc, just like planets around a star. Due to the curvature of space, light rays also bend near massive bodies. Einstein predicted this, and already in 1919, during a solar eclipse, astronomers noticed that the stars around it had shifted slightly. The moon noticeably curves space. This is absolutely counterintuitive, but the geometry of the universe is indeed not Euclidean. And another surprise from Einstein, time flows differently in different places. The stronger the gravity, the slower clocks run. On Earth, time lags slightly behind lunar time. It's hard to believe, but ultra-precise experiments have confirmed this. For example, Gennady Padalko, the record holder for time spent in orbit, aged 0.02 of a second less than his twin on Earth over 879 days in space. Of course, the difference is minuscule, but it exists. It turns out that space-time is not a frozen stage, but a living, moving actor. Masses bend space, and it changes the motion of bodies and the passage of time. Einstein instantly became a rock star. "Revolution in science!" proclaimed the Times headline. "The greatest achievement of human thought," echoed Joseph John Thomson. But you know what's interesting? General relativity did not cancel Newton's physics, but supplemented it. At low speeds and scales, their predictions hardly differ. But the stronger the fields and the faster the movements, the more important it is to consider Einstein's theory. He himself said that his idea is a new step from which old physics is seen as a special case. In short, Einstein didn't just rock the boat for no reason. His ideas still change our view of the world. Mass, energy, space, and time turned out to be inextricably linked in a single dancing tangle. And we are part of it. So next time you look at the stars, astronomer John Michel wondered what would happen if a star was so huge that the escape velocity from it equaled the speed of light. Calculations showed that in such a case, even light could not leave its surface. Michel called them dark stars. But at that time, scientists lacked the knowledge to develop this idea. After all, no one even knew the exact speed of light. Only in 1916 did Carl Schwarzschild, inspired by Einstein's theory, find an exact solution to his equations for the simplest case. A point particle. This approximately described the gravity of a spherical star, and Schwarzschild's solution led to unusual conclusions. It turned out that a supermassive star is surrounded by some magical sphere, now called the event horizon. Outside, the star's gravity is familiar, but inside the sphere, an object that has fallen there can no longer return. Approaching the horizon, an observer would see captured light circling the star, and just before the horizon, it would be torn apart by immense gravity. From the outside, it would seem that time inside a ship at the horizon slows down and stops, although for the astronauts themselves, nothing unusual would happen except for the sad fate of being torn apart, of course. For a long time, everyone thought this was just science fiction, but in 1939, Robert Oppenheimer and his student Hartland Snyder proved that black holes can really appear from massive stars that have run out of fuel. They simply collapse under their own gravity and turn into a black hole. Remnants of giant stars and supermassive monsters at the centers of galaxies. Astronomers have even found a black hole of 4 million solar masses right in the center of our Milky Way. If not for the dust clouds, it would shine brighter than the moon in the sky. Terrifying. But physicists didn't stop there. They took quantum theory and applied it to black holes. Stephen Hawking showed that an ideally black hole violates quantum uncertainty, which means it must slowly emit radiation. It turns out that a vacuum is not emptiness, but some kind of quantum broth, and in the powerful field of a black hole, virtual particles are born in it. One can fall into the hole, and the second can fly away. This is Hawking radiation. Thus, black holes evaporate. A black hole has absorbed go. In 1963, Roy Kerr found a solution for a rotating black hole. It turned out that it collapses not into a point, but into a ring. Passing through it, we enter a parallel universe, or another region of ours, as if through a wormhole. These tunnels in spacetime can connect distant regions or even different universes. Theoretically, one can move through them faster than light, without violating the laws of physics. But if wormholes ever give us the opportunity to instantly travel across the galaxy, will they be able to inexorable arrow? Then for Einstein it more resembled a winding river, flowing at different speeds in different places. If we can move in 3 spatial dimensions, why not travel into the 4th, time? What if there are whirlpools in this river of time that throw us into the past? And can it split into 2 streams, creating parallel universes? Yes, special cases of the theory of relativity allow for such possibilities. Hawking was so struck by this idea that he proposed the chronology protection conjecture. This is an undiscovered law of nature that prohibits time travel. Otherwise, as he joked, where are the crowds of tourists from the future at all important historical events? Just imagine what chaos would ensue if we had a time machine. Everyone would suddenly get rich on Bitcoin, tell Nikola Tesla about wireless charging, try to convince Van Gogh not to cut off his ear. This is perhaps the most useless action one could imagine, but then paradoxes arise. What if you kill your own grandfather in his childhood? How did you even learn the secret of time travel if you heard it from yourself in the future? Can you become your own mother, daughter, and grandmother simultaneously, as in Robert Heinlein's story? It seems only a theory of everything can sort this out. So all these mysteries of black holes, wormholes, and time travel will probably remain unsolved until we understand how quantum effects affect gravity and space-time itself. Only then will we know what awaits the stationarity and immutability of the universe. But his own equations led to the opposite result. The universe simply refused to be static. To ensure the stationarity of this world, it was necessary to introduce the famous cosmological constant, lambda, into the equation. This is a kind of mathematical plug that was supposed to balance universal gravitation and prevent the universe from collapsing under its own weight, as the formulas demanded. The physical meaning and nature of this anti-gravity remained a mystery, but since galaxies hang motionless in space, something must counteract their attraction to each other, Einstein reasoned. Another feature of his model was the finiteness of the universe. What does that mean? What happens if you get into a spaceship with infinite fuel and travel to the edge of the universe? Will you hit a wall with the inscription, "End of the world"? No. Space itself is curved and closed in on itself, like the surface of a sphere. Flying straight all the time, we will eventually return to the starting point from the other side. There are no edges here, and although our world is huge, it has a very specific volume. This is much like how the surface area of the Earth is finite, a strong impression on the mathematician Alexander Friedman. Analyzing the equations of relativity, he came to a sensational conclusion. They describe not only a static universe, but also non-stationary models of an expanding or contracting universe. In 1922, Friedman showed that 3 scenarios for the evolution of the universe are possible depending on the average density of matter. If the density is greater than critical, then expansion will eventually be replaced by contraction. Galaxies will fly apart more and more slowly, as if connected by rubber bands. Then they will stop and, under the influence of gravity, begin to approach each other with acceleration until they merge into a single point, a kind of Big Bang in reverse. At critical density, expansion will continue forever, but with deceleration. Galaxies fly apart by inertia, gradually weakening mutual attractions. And if the average density is less than critical, then the universe expands indefinitely, with continuous acceleration. In any case, the universe turns out to be non-stationary. The distances between galaxies do not remain constant. In other words, the cosmos was not always as it is now. 2 explanations for the vast dispersion of galaxies suggested themselves. Either these stellar islands somehow immediately arose at colossal distances and are now slowly converging under the action of gravity, meaning in the future they will merge. Or, conversely, initially, galaxies were much closer, or even at a single point, and then an unknown force scattered them across space. But in both cases, the universe clearly had a beginning. There was a moment zero when something grandiose happened. Either galaxies suddenly appeared already separated by enormous distances, or they were born in one place, and then a powerful impulse scattered them in different directions like billiard balls after a cue strike. Thus, for the first time at a scientific level, the question of the beginning of the world was posed, and immediately the first spoilers appeared, revealing the main intrigue of the universe. But as with any spoilers, many preferred to wait for official confirmation for the dark night sky. Light from distant galaxies simply hasn't had time to reach us. As for gravity, its influence is limited either by the finite mass of the universe or by the high speeds at which galaxies are receding. They simply overcome gravity. Naturally, this theory generated a host of new questions. What preceded the emergence of the universe? Why did the Big Bang happen? How does the monstrous compression of countless galaxies into a point occur? And isn't the very fact of the universe's birth an act of its creation by someone from outside? Friedman did not know the answers to these profound philosophical questions. Einstein did not accept his idea, although he acknowledged the mathematical correctness of his colleagues' verification was required. Yes, experiments with entire galaxies are impossible under terrestrial conditions, but one could try to measure their speed of movement using the Doppler effect, that is, by the shift of spectral lines towards the red side for recession or the blue side for approach. In 1927, in the mountains of California, Edwin Hubble began his work, equipped with the most powerful 2.5-meter reflector telescope of the time and a modern spectrograph. This instrumentation allowed him to capture the faint light of distant galaxies and analyze their spectra for Doppler shifts. Hubble expected to get a chaotic picture of movements. Some galaxies should have been approaching us, some receding, but it was not to be. It turned out that the nearest galaxy, Andromeda, is indeed moving towards us at a speed of about 100 kilometers per second, but all other galaxies had redshifts indicating their recession from the Milky Way. Moreover, a clear dependence was observed. The farther the galaxy, the faster it flies away from us. This was called Hubble's law. The conclusion was unequivocal. The universe is non-stationary, and the mechanism of expansion. Imagine that galaxies are points drawn on the surface of a balloon. As the balloon inflates, the points move away from each other. Moreover, the farther apart they were initially, the faster the distance between them grows. Regardless of which point we choose as a starting point, the picture will be the same. And could scientists then determine the moment when all galaxies were very close, that is, literally at one point? Yes. Hubble's law made it possible to estimate the age of the universe, that is, the time elapsed from moment zero to our days, and this age turned out to be in the range of 13.7 to 13.9 billion years. Imagine almost 14 billion candles on the universe's birthday cake. It is pointless to look for the point where all matter was gathered at moment zero. It is any point in the universe. Therefore, the inhabitants of any galaxy have the right to consider themselves the center of the world. Both Nicholas of Cusa and Giordano Bruno were right. In your opinion, there was nothing, and suddenly there was a big bang, and from nothing, from a point, the entire universe arose. How can this be? If ancient thinkers wondered about the elements that make up the world, then in the 20th century, the chemical composition of cosmic bodies became known. Analysis of star spectra showed that they consist of two simplest elements, hydrogen, 75% of the mass, and helium, 25%. And all other heavy elements make up only about 1% of stellar matter. This ratio turned out to be typical for the interstellar medium as well. Why is there 3 times more hydrogen in the universe than helium? Where did this proportion come from at all? German physicist Hans Bethe delved deeper and discovered nuclear reactions in the cores of stars, in which one helium-4 nucleus is formed from 12 protons of hydrogen nuclei. That is, if all cosmic helium arose from hydrogen, then its mass should be 3 times less. But there is a nuance. The speed of these reactions in stars is too slow. Over the lifetime of stars, which is 5 to 10 billion years, thermonuclear synthesis simply does not have time to significantly change the initial composition of matter. It seems stars were formed already from a mixture in which helium was developed by George Gamow, a former student of Friedman. Comparing the composition of the universe and models of its expansion, Gamow realized that in the first moments after the Big Bang, the density and temperature of cosmic matter were so high that part of the hydrogen had already managed to turn into helium. At the same time, elements heavier than helium did not arise. The conditions were still unsuitable for them. Thus, the theory of the primary synthesis of elements in the universe was developed by Gamow and his graduate student Ralph Alpher. By the way, Gamow added Hans Bethe as a co-author after writing the article, just so the theory would be called alpha, beta, relying on the laws of thermodynamics, understood that at such a high initial temperature, matter must have been in complete thermal equilibrium with radiation. Calculations showed that in this primary broth of hydrogen and helium, there should also have been photons, and with a huge preponderance, there should have been billions of orders of magnitude more of them than atoms. That is why heavy nuclei could not form. However, as the universe expanded, the energy density of radiation fell faster than the mass density of matter. Gradually, the role of radiation in the dynamics of the universe became secondary. But where did these relic photons go then? Gamow and his colleagues proved. Nowhere. Simply because of the expansion of the universe, the wavelength of primary photons continuously grew. If in the first moment after the Big Bang they were high-energy gamma quanta, then after billions of years of expansion, they turned into microwave radiation. Even today, we should be literally immersed in this thermal radio background, uniformly filling the cosmos. According to calculations, the temperature of this radiation should be in the range of 0 to 10 degrees Kelvin. So, theorists predicted what to look for. Alas, at first, the scientific community simply did not notice. As often happens in the history of science, a brilliant hypothesis, radio astronomers from the Pulkovo Observatory did indeed register a microwave background of the required spectrum, but they did not realize the significance of their discovery. And a little later, the unforeseen happened. Employees of Bell Laboratories, Arno Penzias and Robert Wilson, while debugging receiving equipment for satellite communications, encountered a strange microwave noise. It did not depend in any way on the direction of the antenna or the time of day. In an attempt to get rid of it, engineers cooled the detectors with liquid helium and even cleaned out white dielectric material from under a pigeon's nest built in the antenna. All was in vain. The mysterious background stubbornly poured from all over the sky. Imagine Penzias and Wilson turned out to be the discoverers of relic radiation without suspecting it themselves, and in 1978 they received the Nobel generated by the Big Bang really exists. Its characteristics exactly match the predictions of Gamow's hot universe theory. It uniformly fills the entire cosmos, which confirms the homogeneity and isotropy of the universe even in the first moments of its life. After all, the microwave background itself arose only 1/10,000th of a second after the Big Bang, and began to propagate freely after 380,000 years, when the plasma of the universe cooled and became transparent. The discovery of relic radiation became the second direct confirmation of the Big Bang concept after Hubble's law. No alternative theories from the Earth's atmosphere, receivers for registering the relic radiation began to be placed on satellites. The first such experiment was the Soviet Relikt-1 complex. It took place in 1983 on the Prognoz 9 satellite, but its sensitivity was not enough to discern the fine structure of the radiation. A breakthrough was made by the American COBE satellite in 1989. It turned out that the relic background is not perfectly uniform. It has tiny fluctuations in temperature and intensity. It turned out that the young universe was not completely smooth. It contained minute inhomogeneities in density and temperature. It would seem all logical. Weak density perturbations in the young universe should have been amplified by gravity and generated matter clumps. After all, in regions with higher density, gravity begins to attract matter more actively. This leads to an even greater increase in density. A self-sustaining process of gravitational instability is launched. The initial fluctuation, like a snowball, gathers surrounding matter onto itself. This is how protogalaxies are born, and within them, individual clumps, protostars, and those under the influence of their own weight, heat up and ignite with thermonuclear flame. This idea seems logical, but when scientists try to describe it using mathematics and physics, was that the universe is constantly expanding, and because of this, the density of matter in it decreases. This expansion prevents matter from gathering into denser regions. It's unclear how small clumps of matter could overcome the expansion of the universe and form galaxies. The second problem is related to the fact that the early universe was very hot and dense. Because of this, particles of light, photons, constantly collided with particles of matter, electrons, preventing clumps of matter from growing. Only when the universe cooled sufficiently and electrons combined with protons into atoms did matter become transparent to light and clumps could grow. But calculations show that the clumps that could have formed then do not match what we see in the relic radiation, the echo of the early universe. It turns out that ordinary matter made of protons and electrons cannot explain the observed structure of the universe. Came from an unexpected direction. It turned out that besides ordinary matter, the universe is filled with a completely different substance. Dark matter. Its existence was independently inferred from anomalies in the rotation of galaxies. Astronomers had long noticed that spiral galaxies rotate somewhat incorrectly. Stars on their outskirts move just as fast as those in the center, resembling the rotation of a wheel. To explain this, it had to be assumed that the visible matter of galaxies is located within invisible matter, the mass of which is 5 to 6 times greater than the total mass of all stars and gas. It turned out that galaxies are like icebergs. Only a small part of them is visible, while the lion's share of the mass is hidden from view, manifesting itself only gravitationally. This mysterious substance was called dark matter. But what is it? The option of invisible objects made of ordinary matter was quickly dismissed. Their mass is insufficient. It is much more natural to assume that dark matter is some new type of fundamental particle. Apparently, they participate only in gravitational interaction, but know neither strong nuclear nor electromagnetic forces. Therefore, these particles cannot form atoms and do not interact with radiation. They freely penetrate ordinary matter. Right now, dark matter is passing through your body. Creepy, right? Physicists have already come up with a general name for these particles. WIMPs, weakly interacting massive particles. The main candidate for the role of WIMPs for a long time was considered to be hypothetical supersymmetric partners of ordinary particles, neutralinos. Alas, their traces have not yet been found at the Large Hadron Collider. Now the main hopes are pinned on other options, axions, sterile neutrinos, and Jim Peebles realized the cosmological role of dark matter. The temperature of the relic radiation reflects the distribution of ordinary baryonic matter in the young universe, but not WIMPs. The latter had already begun to gather together under the action of their own gravity, and when baryons cooled and became transparent to radiation, they simply fell into the prepared gravitational wells of dark matter. Thus, clumps of dark matter were able to develop unimpeded, becoming the seeds of future galaxies. Eventually, visible matter settled into the potential wells of these seeds. Computer modeling of the universe's evolution, taking dark matter into account, yielded stunning results. Theoretical calculations perfectly matched the data from the Planck probe. Moreover, the calculations reproduced the cellular structure of today's cosmos. Superclusters of galaxies form, as it were, the walls of bubbles, and inside these bubbles there is almost nothing. We have truly understood how today's cosmic structures arose from the homogeneous early universe. Now all that remains is a small matter, to catch dark matter particles in experiments. This will allow us to establish the specific physical nature of the elusive WIMPs, although it cannot be ruled out that dark matter will turn out to be something completely different come together. We have finally grasped the secrets of the universe. Most scientists were forced to admit the non-stationarity of our universe. Some met this with hostility, others with enthusiasm. There are still people who deny the Big Bang and consider it a ridiculous invention of scientists. Heck, some commenters still believe the Earth is flat, but even the most ardent supporters of the Big Bang theory admit that it has serious problems. The main one is the horizon problem. Let me remind you that the relic background is striking in its homogeneity. Its temperature in all directions coincides with an accuracy of hundredths of a percent, and the tiny fluctuations are also the same everywhere. Imagine that we pointed a radio telescope at section of the sky A, and then at section B in the opposite direction. Why are the relic signals from A and B so similar? After all, the distance between these regions today is about 90 billion light-years. That is, A and B could not have conspired and influenced each other in any way. Since the Big Bang, light has only had time to travel 13.8 billion light-years. That is, only points no more than this distance apart can be somehow connected. This limit is called the horizon. How then to explain this amazing consistency of the relic background in all directions? Even if A and B were much closer in the past, a signal between them still would not have had time to propagate. A and B were never causally connected. But why do the conditions in them coincide with incredible accuracy? Another problem what is responsible for flat geometry of the universe? According to Friedman's models, the future fate of the world depends on the average density of matter. If it is greater than a certain critical value, gravity will sooner or later stop the expansion and force the universe to contract back into a point. If the density is below this mark, the expansion will be eternal. But the Big Bang could have produced any amount of matter and radiation. Why did the average density of the cosmos turn out to be so close precisely to the critical value? The chances of coincidence are negligible. At critical density, the universe has zero curvature and unlimited volume. This is flat geometry. What kind of perfectionist so carefully adjusted the initial conditions so that after billions of years, the density would be close to critical with an accuracy of 15 the universe expanded not by inertia, but with acceleration? This would solve the horizon problem. Then an initially causally connected region could have flown apart so quickly that its fragments lost the ability to exchange signals. But what could provide such accelerated expansion? A hint came from Einstein. Remember, he introduced the cosmological constant into the equation, the very anti-gravity, to make the cosmos static. Einstein himself called this his greatest mistake. But subsequently, scientists wondered if something similar really existed, and if this force outweighed the usual attraction of masses, then the universe would expand with acceleration. Curiously, as early as 1917, astronomer Willem de Sitter considered a model of an empty universe containing only the cosmological constant, and showed that in such a world, two bodies would accelerate away from each other, and the acceleration would be faster the greater the distance between the bodies. It turns out this force does not weaken with distance, but rather increases. Isn't this the key to the mystery of the accelerated expansion of the early universe? However, neither Einstein nor de Sitter could say what exactly creates anti-gravity. It turned out that this is simply a property of the very space of the universe. But then we again have to reconsider the notion of space. The cosmos is filled with fields. Any point, even an empty one, can attract or repel particles placed in it. This means fields, and with them space, contain energy. What used to be called emptiness, physicists call a vacuum. But this is by no means a synonym for nothing. A vacuum is an active medium permeated by energy-intensive fields, and perhaps it is the energy of these fields that provides the anti-gravity, causing the accelerated expansion is this. Immediately after its birth, the universe experienced a brief period of very rapid, exponential expansion. This initial phase of inflation lasted a negligible fraction of a second, but during this time, a tiny region of space measuring 10 to the power of minus 27 centimeters increased by 27 orders of magnitude, reaching a diameter of about 1 centimeter. According to the inflation hypothesis proposed first by Alexei Starobinsky and then developed by Alan Guth, the cause was an exotic state of matter, that is, a high-energy vacuum. Unlike our usual vacuum, this initial vacuum possessed a colossal energy density. Each cubic centimeter of it weighed as much as the moon. Such a supervacuum generates enormous negative pressure. Anti-gravity, 3 times greater than the usual gravity of matter. Under the influence of this anti-gravity, any lump of high-energy vacuum will begin to expand rapidly. Every 10 to the power of minus 38 seconds, its dimensions will double. This is what happened to the progenitor of our universe. Okay, but why then did this hyperinflation stop and give way to normal expansion? Physicists believe that the initial vacuum is unstable. It inevitably decays, transitioning to a normal state with low energy density. According to Einstein's formula, E equals mc squared, the excess energy transforms into the mass of elementary particles. Quarks, leptons, photons, etc. Thus, the high-energy vacuum, as it were, evaporated, giving rise to the familiar matter and radiation of the early universe. It is this decay that is perceived as the Big Bang. In a gigantic flash, almost all the contents of our world were born. Nuclear particles, electrons, neutrinos, quanta of light. This put an end to anti-gravity. The high-energy vacuum was no more. Therefore, after the Big Bang, expansion slowed down, obeying the usual gravity of the newly born particles. However, the enormous inertia of inflation did not disappear, and expansion continued, albeit at a slower rate. The puzzles mentioned earlier. The horizon problem, that is, the homogeneity of the universe, is resolved simply because in the inflationary scenario, different regions of our universe indeed had a common past. They were close together inside a tiny bubble, and only then were they carried apart to gigantic distances. The same applies to the problem of the flatness of space. Inflation was so powerful and rapid that we simply do not notice the global curvature of the world, just as an ant does not feel that it is crawling. To measure the distance to nearby galaxies, Hubble used the method of standard candles, that is, objects of known luminosity, called Cepheids. But how to determine the distance to distant galaxies, which are visible even in the best telescopes only as faint specks? New beacons were needed, and in 1977, astronomer Yuri Pskovsky proposed using type Ia supernovae for this. They arise from the thermonuclear explosion of a white dwarf. Perhaps this is the most dramatic way to declare one's existence. The luminosity of a supernova is comparable to the glow of billions of stars in a galaxy. They are rare, but in the gigantic volume of the visible universe, they flare up quite often. In 1998, Brian Schmidt and Adam Rees published stunning data on 16 supernovae. It turned out that their brightness was lower than expected for the measured redshift. This means that these galaxies are farther away and receding faster than Hubble's law predicts. The acceleration graph clearly curved upwards. A year later, Saul Perlmutter's group confirmed this result with 42 supernovae. Something was clearly accelerating the galaxies, causing them to fly apart with increasing speed. A repulsive force, anti-gravity, is acting in the universe, increasing with distance. In 2011, Perlmutter, Schmidt, and Rees received the Nobel Prize to change the understanding of the world. If before the debate was only about whether there was enough gravity to stop the expansion and collapse of the universe, now it became clear. Expansion will be eternal due to the dominance of anti-gravity. Galaxies will continue to fly apart, losing the ability to see each other. So what causes this acceleration? This unknown force was called dark energy. The first hypotheses about its nature used developments from inflationary theory. Remember how after the Big Bang, the superenergetic vacuum turned into an ordinary vacuum with zero or negligible energy density? Well, the acceleration and expansion hint that the energy density there is still higher. Apparently this is dark energy, or Einstein's cosmological constant. In this model, it uniformly fills the entire universe and intergalactic space and is not diluted. Its density is constant in space and time. It does not interact with matter. Calculations showed that about 7 billion years ago, the average density of matter fell below the density of the vacuum, and since then, the universe has been expanding with the following composition of the universe. Dark energy around 70%, dark matter 26%, and all other baryonic matter, i.e., ordinary matter, only 5%. Astonishing. Astronomers have studied only 0.5% of the universe's mass for 2,500 years. But what exactly are dark matter and dark energy, which make up most of our world? Strictly speaking, we do not yet know. But right now, scientists are working on hypotheses that will probably soon shed light on this as well. We are lucky to live in a unique era when the universe has already cooled enough for complex structures to appear, but has not yet had time to fly apart so much that galaxies lose sight of each other. Expansion will continue forever, accelerating to the limit set by the density of dark energy. Galaxies will recede until they turn into unreachable islands of light. The last stars will burn out, and the cosmos will plunge into twilight, illuminated only by rare supernova flashes. And after unimaginable quintillions of years, even black holes will evaporate and turn black, leaving only cold emptiness in the universe. Brrr. Of course, this is still just a scientific model, not firmly established facts, but this is precisely the picture that modern cosmology, the fruit of centuries of labor and insights of thousands of scientists, paints for us. And who knows, maybe our minds appeared just in time to, by looking into the abyss of the future, find a super dense vacuum that gave birth to our universe come from. Maybe it arose in the depths of some other world, and does that maternal reality exist now? What if right now in our cosmos the embryos of new universes are being born? The honest answer for now is one. We do not know, but science has some ideas. For physicists, the mechanism for the appearance of clumps of high-energy vacuum does not look overwhelmingly complex. If we could look into the microworld with a magnification of 1 billion times, we would see how virtual particles, ghostly portions of matter, are born and immediately disappear at every point in space. It's like the motivation to exercise every morning. Usually these particles annihilate almost instantly, emitting quanta of light, but if a sufficiently powerful field is nearby, it can separate these particles before they disappear. Then they will become quite real, as if arising from nothing, although in essence the energy of the external field will create them. In the quantum foam, all sorts of particles constantly arise, including those corresponding to an unstable vacuum. One fluctuation is enough for the expanding tension of the vacuum to unfurl a pocket of spacetime hidden within it into an entire universe. Such an event is unlikely, but not impossible. But where does so much energy come from in a tiny particle to turn into the mass of the Big Bang? For clarity, let's recall black holes. From the outside, they look compact, but inside they hide a monstrous supply of mass energy. Gravity once gathered and compacted a huge amount of matter into an extremely small volume, pumping colossal energy into it. It is enough to curve and tear the fabric of spacetime at this point. It turns out that even if an object seems tiny from the outside, the special geometry of its internal spacetime is capable of accommodating an entire universe with enormous energy content. Perhaps our cosmos is just the interior of a black hole in an unknown external world. This is not excluded, although not proven. In principle, a supermassive particle, called a Friedmann, can also hide an endless universe within itself. To an external observer, such an object will look like a negligible fluctuation, although by its own clock, it can even now microworlds are constantly being born in our universe. Paradoxically, this is possible. You might think this is nonsense, but physicists treat this absolutely seriously. One of the options for the origin of universes was proposed in 1983 by physicist Andre Linde. According to his theory, a rapidly expanding parent universe continuously generates similar microworlds, and the distance between them immediately increases. As a result, an innumerable family of worlds arises, each of which can also fragment during its own accelerated expansion. In such a model, there can be countless universes. Then our cosmos is just one of the bubbles in the giant foam of the multiverse. The idea of the multiverse explains how it happened that life was able to originate in our universe at all. After all, if we go through all conceivable variants of fundamental properties, from particle masses to world constants, it turns out that almost all of them are incompatible with our existence. The slightest deviation of these parameters from their current values and the universe would become lifeless, even without atoms, stars, and planets. It seems as if someone specially adjusted the cosmos for future observers. One can imagine a higher civilization that configured our universe by launching inflation from a correctly formed vacuum clot. It is possible that someday Earthlings will also learn to program microworlds through controlled matter collapse. There is another explanation. After all, if the multiverse generates all possible combinations of fundamental properties, then among this diversity, unlikely variants such as our world will inevitably be found. Somewhere, a random fluctuation will necessarily produce a set of physical parameters ideally suited for the emergence of complex structures, stars, planets, galaxies, life, and reason. Therefore, there is nothing surprising that our universe is so friendly. If it were different, we would not be here, and there would be no one to be surprised. The multiverse truly boggles the imagination. There's a possibility that somewhere out there, an immortal version of me exists. In our universe, I am still working on that. However, not all scientists share the concept of the multiverse. Any sound hypothesis should offer a way to test it experimentally, but parallel universes by definition cannot affect ours. Therefore, their existence is fundamentally unprovable. No thought experiment or real experiment can detect neighboring worlds. So, is it worth talking about them seriously at all? On the other hand, in recent years, scientists have increasingly encountered hypothetical objects that do not directly contradict physical laws but are inaccessible to experiments. We seriously discuss dark matter, primordial black holes, or wormholes. In essence, these are also entities beyond direct verification, at least for now. Ideas about the multiverse and multidimensional spacetime should be perceived at least as powerful computers are calculating the most complex models. Telescopes tirelessly catch signals from the sky. Accelerators and colliders penetrate the depths of the microworld. Scientists compare their hypotheses with measurement results, striving to find the truth. Step by step, science is approaching an understanding of the fundamental foundations of the universe, and yet skeptics do not relent. How? Scientists still know almost nothing about elementary things. What caused the Big Bang and what was before it? What are the mysterious dark matter and energy made of? How many parallel universes are there in total? Should I take an umbrella? Yes. While our knowledge is not perfect and not complete, it is growing. Since the era of Giordano Bruno, the volume of accumulated knowledge has grown by orders of magnitude. We are already discussing hypotheses trying to explain dark energy and dark matter. We have proposed the idea of a multiverse. We are discussing the paradoxes of the anthropic principle, but these are still only hypotheses. Further research, if not tomorrow, then in 400 years, will provide answers to these and other, perhaps not yet posed, astonishing questions. Science will find answers to them. The pace of scientific progress is accelerating. It is difficult to even imagine what discoveries await our descendants in the coming centuries. They will look at the ideas of the 21st century in the same way we look at the conjectures of the Middle Ages. Fortunately,